we're going to learn about the concept of the memory hierarchy, organization, and also the types of the input and output devices. So we're up to the task, and so here now getting to understand the basics about the computer organization or the basic the von Neumann architecture. The von Neumann architecture here is one of the models in the computer systems, which is you're able to store or which uses a single memory unit to store the both programs and also instructions and the data. So which means is you're able to get given your the processors like the central processing unit and the memory of the computer system, be the storage and also process the sequential instructions, and also the input and output devices, the input and output devices. Then how are you able to create the connections with those devices for you to allow the data and instruction to be processed? So the architecture, the von Neumann architecture, it was first published in by a guy called the John von Neumann in 1945. So this architecture, you're able to store your computer programs, and also you're able to store the instructions and the data and also the programs in the computer memory. So basically, the von Neumann architecture is designed to be able to handle the aspect about the memory, the computer programs, and the instructions. So the key components which you need to understand about this the von Neumann architecture is about the processor, which is the central processing units. It can be the microprocessor, then the input and output devices, which are now interconnected with what we call the system bus, for those sequential data instructions. You're able to process your data in real time, which allows you to process your data instructions transferred between them. So it consists of the control units, what we call the system bus, and also the arithmetic and the logic units, where you're able to do the logic mathematical operations, like the add and subtraction, and also we have the logic unit, which are able to understand the aspect of using what we call the digital devices, the digital electronics, or those digital gates for you to be able to perform instructions. So that's the concept, the ideal behind the von Neumann architecture. So this von Neumann architecture here is what we talk about the modern computer systems, where now you're able to process those instructions. You're able to, which means now, given the CPUs, you're able to fetch those instructions and also the data in the same memory using what we call the pathways. So here, this von Neumann architecture, when we talk about the components, or what we call the systems, or the memory, or the instructions, or the program instructions, is divided into two types. What we call the fixed programs, where you're able to, the function is specific. They couldn't be programmed, each characters. So which means now they have some limited capability. So which means now the program which cannot be programmed, it has some limited capability. Then that's what we call the stored program computers, which now is able to, it has a memory capability, and it can be programmed to carry out many tasks sequentially. We can talk about various applications stored in them. Hence the name stored programs, sequential. You're able to process more instructions. You're able to store your data, and also you are able to have that orchestration of the memory spaces. So this the von Neumann architecture, it consists of the central processing unit, the CPU, which is the processor, which is the brain of the computer system. And the brain of the computer system is divided into the control unit, the arithmetic and logic unit, ARU, and also we have the registers. So for the control unit, you're able to fetch instructions and the data from the memory, and also you're able to decode. The aspect of binary encoding, the binary encoding, you're able to encode your sequential programs to other system components. Then we have the arithmetic logic unit, which you're able to, it performs all the arithmetic operations. You can be able to add, and you can be able to subtract, and also the comparisons, what we call the logics, where you are able to use techniques such as the logic gates. The logic gates like the AND, the OR, the NOT gates, the exclusive OR. As you proceed in your academic landscape, you are going to understand about this aspect of digital electronics. How do you process, given an input value of A and given another input value of P, then how are you able to get the corresponding values given the binary encoding of numbers of zeros and ones? Then we have the registers, which now which is smaller, and also is a fast storage location within the CPU for holding the data and instructions currently processed in the computer systems. So you're able to, it's a small device, it's a small storage device where you're able to hold data and instructions. So which means you're able to store your data, which now you're able to process instructions and the data given the location when they're located within the CPU or the CPU processor. Then another component of the von Neumann architecture is the memory unit, which now this memory unit, sequentially you are able to store both programs, instructions, and also the data. So that's the aspect about the memory unit. So as we proceed with this, this program, you are going deeply to understand about what is this memory unit. How does it store the data? Yeah, how does it store the instructions within the computer program for you to be able to process it? For you to be able to process instructions. Then another aspect, another component of the von Neumann architecture is the input and output devices, which allows the computer to be able to communicate with the outside devices, outside world. Talking about the keyboards, the monitors, those the output devices and the inputs, the keyboards, the hard drives, where you're able to store your devices or you're able to store your data. Then the last component of the von Neumann architecture is the bus, the system, what we call the system bus, which now provides what you call the communication pathways, which you're able to connect your components, including the data bus, and also the address bus, and also the control bus. As we proceed, you are going to understand what is it about the data bus, what is it about the address bus, and what is it about the control bus. Then how you're able to use them for you to be able to orchestrate, information flow, sequential data processing within the central processing unit. Yeah, so those are ideally the basic components when we talk about the von Neumann architecture. So these components also, talking deep about this, the components, like the central process unit, which is a CPU, is what we call the control. It's what we call is the main part of the computer system that controls how the CPU works. It is made up of the control unit, the main memory, of course, for storage, we call it the primary memory. Then we have the arithmetic logic unit, of course, which are able to do various arithmetic operations. And also the CPU handles the instructions from the programs and also process the data, store the information, and also produce the results. So without the CPU, the computer cannot be able to perform the tasks. So this is the architectural, or this is the service or the architecture about the CPU. We have the memory for storage, then we have this address, we have the data, this information, the data, we have the control, we have this is the PC, this is the instruction register. You're going to understand about this as we proceed with the session. Then of course we have the system bus, the system bus, which also you are able to process your binary in the input and output bus. You have the interface, which is more of the input and output interface, and also we have the device. This is the kind of the heuristic view, or what we call the architectural framework, or what we call the architecture for the CPU, or for the CPU operation. When we talk about the device like the PC, this is what we call the program counter. Yeah. When you talk about the ER, this is the instruction register. How do you able to store your instructions? Are you able to store what we call? Are you able to register your instructions? Data and instructions. What you call the MAR, what we call the memory address register. So how are you able to store in terms of the location access your stored data or instructions? Then you have the MDR, which is the memory data register. Then how are you able to temporarily hold your data sets? Then we have the accumulator, which you are able to also provide what we call the arithmetic and logic operations. And also we have the purpose, the general purpose. So ideally here, the concept which you need to understand about the CPU system is the aspect of is there people who haven't allowed to join in? Yeah, let me admit all. Yeah, I think all are admitted. Yeah, great. So here, given given your device, or given what you call your central processing unit, or the CPU, which is the main process of the computer system, are you able to store your files? Are you able to store your data, given the memory here? And we have the arithmetic logic unit, which now, given this arithmetic logic unit, you are able to do various operations, which I've already alluded to. You're able to add, you're able to subtract, perform various, and also the logic units, which are able to use the mathematical operations, or the logic gates, or the circuits like or what we call the logic circuits, such as the AND, the exclusive OR, for you to be able to perform those arithmetic operations. I've talked about the MRA, which MAR, which is the memory register. Yeah, what are these memory register? We have the MDR, which is the memory data register. Then we have the accumulator. What is it about? So you're going to learn about that. We have the interfaces, the input and output bus. Those are ideally the techniques which you're able to really perform what we call various sequential tasks within the CPUs. So generally getting to understand about those terminologies, talking about those components, the CPU, which is now embedded with the control unit, which now sequentially you're able to manage how the processor works. That's the CPU, by setting the signals, the control signals. So it decides how the data should be moved. How should data move within the computer system, given your control signals, and now given your input and output operations. Then how you're able to fetch those instructions from the memory for execution. Yeah, that's more of the control unit. About the arithmetic logic unit, you're able to perform the arithmetic and logic operations, which now, given the CPU, you're able to handle various calculations for decision making. Yeah, so if we talk about the logic operations, the AND gate, so which means that now sequentially, you're able to process various logic operations. Of course, talking about arithmetic operation, of course you can be able to add, subtract, and perform various operations for decision making. Also, using the logic operations such as comparisons, and also what we call various tasks such as the bits, those binary bits within the data sets, which means now you're able to handle with other digital electronic devices such as the OR gates, for you to be able to process for current to be able to flow. Given because these are electronic devices, which means now this is what we call the sequential current flow. Then those components allow the sequential instructions to be processed within the CPU system. Then we talk about the registers. These registers, they are the type of memory located within the CPU, which now they temporarily store information. So talking about the registers, you are temporarily storing the information that the processor is currently working on, which means they're making the program execution and operations faster and more efficient. So these registers, they serve as the CPU is primary working memory. So don't forget about this. We use the registers for temporary storage of information. Now, these registers are embedded with the program counter. And this program counter, it keeps track of the address of the next instruction to be executed. So talking about the program counter from there, you have seen from the architectural CPU system there, for sequential instruction processing, it keeps track of the addresses, the memory modes, the memory addresses for the next instruction to be executed within the CPU system. Then we have the ER, which is the instruction register, which now you are temporarily or you are holding the current instruction to be executed. That's the aspect, or that's the instruction register within the register, which is a temporary storage for your processor. Then we have the MAR, which is the memory address register, which now you're able to store the address of the main or for the location, or what we talk about the location of your data. Yeah, where do you locate your data? You are able to store the aspect about the storage of your addresses and also the location. How are you going to access your data within the CPU system? Then, of course, you have the MDR, which is the memory data register, which now you are temporarily holding the data being transferred to and from the memory. So, which means now, so it was what we call the data priority, which means now as you process your data sequentially, so it temporarily holds that data as now the sequential processing of your data and instructions, fetching those instructions within the CPU works. Then you're able to get your inputs or the outputs, the results within the monitor or your hardware device. Then we have the accumulator. So the accumulator, ideally the accumulator you're able to register is a register that stores immediate results of the arithmetic and logic operations. So we use the accumulator for you to be able to register your instructions, or it's a register that stores intermediate results of arithmetic and logic operations. Finally, within the register, we have the general purpose registers, which now they're used to store the temporary storage, acts as a temporary storage for the data during the processing. So it kind of acts the same like the memory data registers, where you're able to hold that temporary data transfer within the computer memory. Yes. Then, of course, the continuation with this the von Neumann architecture, we have another aspect of the bus, what you call the system bus. So this system bus is a communication system that transfers the data. Yeah, so don't forget about that. So this the system bus is a communication pathways that you are able to transfer the data and addresses that controls the signals between the CPU, the memory, and also the input and output devices. So here, the von Neumann architecture, in a von Neumann architecture, a single bus is shared for both data and instructions, which can create a bottleneck known as the von Neumann bottlenecks. So under the bus, the system bus, we have the input and output bus, of course, which is alluded clearly from here, from this architecture of both the CPU, yeah, the input and the output bus. What is it about? So this input and output bus, that's what we call the interface, input and output interface, which now you're able to connect to the CPU and the memory to the input and output devices. Then we have the device, which now refers to the external hardware, yeah, like the keyboards. So then, given this, these instructions, this sequential instruction being processed from the registers and from the registers, then how are you able to really how are you able to interact with those devices? It means now that sequential instructions, you must be able to feel from the aspect of the devices. How do you interact with those hardware devices, given what we call the interfaces, or what we call given the data and instructions now processed from the CPU or from the processor, which means now given the output devices or the external hardware devices, such as the keyboards, the monitors, and the storage devices, then you're able to interact from the sequential instructions and the data which has been processed from the processor or from the CPU. Then, of course, the key characteristics of this the system bus is we have the single memory for data and instructions, which means both the data and the program instructions are stored in the same memory. Then we have the shared bus, which means now a single bus is used for transferring the data. Here, given the addresses and the control units, you can be able to we use the shared bus for you to be able to store the aspect of transferring the data and also the addresses and the control signals. And then we have the sequential execution, which means now, given the data sets or given your instructions, then how do you able to execute one task at a time in a sequential manner, which means now what you call the FIFO, when you're going to learn later about the data structures and algorithms. So what we call the FIFO principles, the first in, first out. Yeah. So which means now the first in, the sequential execution, means now the first task to come in to be executed. Then that sequential processing is what allows for that kind of for that program instructions or for data processing. Yeah. So here, of course, now mentioning about the von Neumann architecture. Mentioning about the von Neumann architecture, which is now one of the key concepts in terms of storing both programs and instructions and the data within the computer system. One of the things which you need to understand about this the von Neumann architecture is the backbone of the modern computing system. Yeah. Is the backbone of the new modern computing system, which means it outlines how the computer works with the central processing unit, the memory, both the primary memory and the secondary memory, and also the input and output devices of all the connected by the system bus. Then this design allows for flexible programming and also efficient data processing. Yeah, that's the aspect which you need to understand here about the von Neumann architecture. So it introduces the key concepts such as the fetch, decode, and execute cycle, which means a shared memory for data and instructions and the stored programs. These ideas form the foundation for more advanced topics in the computer design. So the keyword here which you need to understand about this, the von Neumann architecture, is the backbone of the modern computing. And given the computer networks or the computer systems, you're able to store, you're able to handle the central processing unit, both the main and the secondary memory. Yeah, your input devices connected to the system bus, and now allow you for flexible programming and also for efficient data processing. Here now, you are able to sequentially handle the fetching, decoding, and execution of your data and instructions shared within the memory. That's the ideal aspect about the von Neumann architecture. Of course, so talking about these key components, of course, how are they interconnected? Talking about the central processing unit and the main memory or the memory unit and the input and output devices. So for you to get the connections you have to use what we call the system bus. And now this system bus, it allows you to be able to transfer the data and the addresses and also the control signals for you to be able to process your data and instructions. Don't forget about that. Yeah, don't forget about that. Then that's what we call the CPU, which is the brain of the computer system responsible for executing instructions and also performing computations from the control unit to arithmetic logic unit. Then that's what we call the memory unit, which you're able to store both the data and the instructions, allowing the computer to be able to access and also manipulate the information. That's what we call the input device, such as the keyboard and the mouse, which allows the user to be able to enter the data and also the commands. While the output device, such as the monitor and the printers, to display the outputs, the results. Of course, now that's what we call the system bus, which now it provides what we call the communication pathways, for you to be able to transfer your data and also the control signals between the CPU, the memory, and also the input and the output devices. Yeah, so that's ideally the technique behind that's the idea, the technique behind this interconnection of the von Neumann architecture. Yeah. Okay. Yeah, Benjamin, mute your device. Yeah, make sure you mute your device. So here now, so take here this into consideration. As we focus on this von Neumann architecture of the von Neumann model, how does it work? Yeah. In the production environment, how do we use this von Neumann architecture model? How does it work in the production environment? First, it starts with the CPU fetches an instruction from the memory via the system bus. We start from there. Then it has the control unit, which are able to decode the instructions. Then, if the instruction requires it, then the CPU fetches this instruction necessary for data from the memory, which means now, so given the sequence of instructions or the data, then you're able to fetch those instructions from the memory via the system bus, which now you're able to orchestrate using the main memory or the memory of the computer system. Then, yeah, let me add somebody trying to join in. Yeah. Yeah. Then that's what we call the arithmetic logic unit, which now you're able to perform those mathematical or mathematical operations within your data. Then you're able to store the results is stored back in the main memory, or the register. Then the cycle repeats each instruction in the processing, that sequential processing, that cycle, for it to be able to, that cycle from fetching to decoding, then that as sequential aspect of decoding and also fetching and storing your instructions or your data. Then what is the significance? The model is fundamental to modern computers because it allows for versatile design where the software can be changed by simply loading the program into the memory. Then is the basis of modern programming languages, and of course, for predicting the performance across the different sequential architectures. Yeah, that's the aspect for the von Neumann architecture. Then, what are the applicability? How do we use it in the production environment? Somebody's trying to join in. Yes, Muhuzo Kilonzi, I see you have raised your hand.
Thank you, Mwalimu. I did not understand how it works. The recent slide.
Okay. Let me demonstrate it clearly for you to be able to understand it clear. Yes. So here, one of the key aspects which you need to understand about the von Neumann architecture is about the aspect about talking about this as the backbone of the modern computing. It means now, how do you able to process your central processing unit, which is the CPU, and also the main and this and the secondary memory, and also the input and output devices. So which means now, given those components, how are you able to fetch the instructions? Fetching instructions now here is of course getting the sequential instructions. Decoding now, it means now, given what we call the binary series of numbers. The binary series of numbers are like the discrete values of zeros and ones, because now for the processor to be able to process instructions is in form of binary series of numbers. Those discrete numbers in form of zeros and ones. Yeah. Then execution cycle, it means now you are able to, the key concept here is given these instructions from the memory is for storage for the system bus. Of course, the system bus here, you understand it from the aspect of that communication pathway. Yeah, for you to be able to transfer your data and also control signals. You get the point? Then the control unit here now, given the instructions, decoding now, it means now, given those binary series of numbers, you're able to perform what we call the decoding. Decoding now, it means now, that's aspect of sequential processing. Decoding, which means now, you must be able to turn your numbers, those binary series of numbers into instructions for processing. Then these instructions, which means now, you use what we call the arithmetic logic unit, ARU, the arithmetic logic unit, for you to be able to perform what we call the mathematical operations. And this mathematical operation can be able to add, you're able to subtract, and also the logic units where you are able to use what we call the digital circuits, or digital devices, or digital components, or digital gates, like the NOT, the OR gate, the exclusive OR, for you to be able to register the data in your computer program. Then this instruction now, it means now you must store this instruction in the memory and using what we call the system register. Yeah, so you store this instruction there in the memory. So here now in the memory, it means now you're able to store the aspect of storage, which means now after storage, it means now you're able to use the registers for you to be able to ideally, temporarily, of course, store your information. So we use the register for temporarily storing your data or your instructions in the computer for them to be able to, for you to be able to execute for that sequential execution. Somebody's trying to join. Let me add up. Somebody trying to join in. Yeah, who else is trying to join in? Yeah. Then, that aspect of storage, you store it using the memory and also all the registers. So the register here, it acts at what we call the temporary. where you are able to store your information or the information in the processor temporarily, yeah, or for making that execution and also the operation faster and more efficient within your CPU system. I think that's clear. Are you able to understand the concept clearly?
Yes, Mwalimu. Thank you.
Oh, great, Kronzi. Yeah, great. So let's talk about the applicability. What are the applications of the von Neumann architecture in the modern computing system? First, given your personal devices, or what you call the digital devices in the computer system. Somebody's trying to join in. Yeah. Yeah, so here now the applicability is this. For the von Neumann architecture here, given the personal computer system or the laptops, and most of the PCs and the laptops, like the Intel, those are the manufacturers, the Intel, the MAD. They use what we call the shared memory that stores both the programs and also the data, enabling efficient running of the software, like the Windows and also the browsers. For example, we talk about the Intel Core i7, AMD, Ryzen processors. Of course, now this is about the industrial production. What are these, like how does it apply in the modern computing? It means now the aspect about processing. Somebody's trying to join in. Yeah, okay. I think all on board. One of the key aspects which you need to understand here is this. In terms of personal, we use the application for the von Neumann architecture in the modern computing, whereby now we use in the personal computers and the laptops, where now we use what we call, the Intel and AMD, which now uses what we call the shared memory for them to be able to store and both the instructions and the data, enabling efficient running of the softwares like the Windows and also the browsers. An example is Intel Core i7 or AMD lesser processors. Those are the manufacturers, or those are the main manufacturers of these hardware devices. Then we talk about the smartphones and the tablets. Of course, you have the ARM-based devices use what we call the shared memory to support multitasking and also power efficient in the apps like the iOS and the Android. For example, we talk about the Qualcomm Snapdragon, the Apple A series chips. Yeah, of course, you get like this architecture, this von Neumann architecture. It applies in the mainstream industry, whereby now you get like the main tech powerhouse in this hardware manufacturers. We talk about the Apple, like they're able to process the different chips for these processors, like the Qualcomm Snapdragon, those series, and also the Apple A series chips. Of course, we can add like the NVIDIA chip manufacturers, which are able to manufacture like the AI processors, which also you can be able to deal with maybe robotics and many more. Of course, you have the embedded intelligent device. This is what the device which, of course, remember the class lab. You were able to see it yesterday, but we didn't have the session. I mean, I think next week I'm gonna bring it. I think you're gonna interact with these devices. Don't you think so? Yeah. How does it work? That microcontrollers or microprocessors. Yeah. You get to interact with those devices. Talk about the Arduino, the Raspberry Pi. Yeah. And also the sensor data sets or the sensor devices. You interact with them. Yeah, because now in this domain of being data scientist, So you're going to apply them later now when you are able to deal with, AV simulations. Yeah, what we call the digital twins. Yeah, how are you able to orchestrate these embedded intelligent devices given what we call your heterogeneous data sets? Maybe you're working on a project focusing on you are trying to improvise a drone to monitor what we call one animal conservancy, or what we call what we say somebody's trying to join in and this is that limitations for them to join. Yeah, I think that limitations. Yeah, but next week we'll have the physical sessions. I think with these devices, this kind of limitations in terms of the users who are able to access these devices or the link and to join in real time. But I think there's a recording which you're going to get later. Yeah. Yeah, so let me make it clear. So as you proceed in your academic landscape, you're going to interact this. So next week when I come, I'm going to bring these embedded intelligent systems, devices like the Raspberry Pi. You interact with it, and also the chamber wires. How you're able to connect and process. So like you can be able to use with other machine learning models, like the deep learning models, to do what we call complex tasks. Of course, we have a series of data analysis like the Monte Carlo simulations, which you can be able to use in terms of doing precision or smart farming. Yeah, you can be able to advise the farmer using these drones, whichever the drones or these embedded intelligent devices. What is the type of the soil moisture which is good in planting a certain seedling? Yeah, maybe you want to monitor what we call like you want to liaise with the Kenya Power. Are you able to help Kenya Power to be able to monitor what we call their smart meters? Checking in what we call the fluctuation in terms of those smart meter monitoring systems. Yeah, so it's really a lot of applicability in the industry. So using this embedded intelligence system, when you combine your data science domain with this embedded intelligence system, then you find yourself to be much more relevant in the production environment. You're able to really outshine, and also not only you can also come up with your homegrown solutions to address a lot of use cases. Yes. Yeah, somebody trying to join in. Okay. Yeah. Sorry for these limitations. I know we are facing others out, but I'm going to share the notes with you after the presentation. Of course, they don't have any complexities. You can go through them. So let me rush a little bit. Of course, I can speak more and more about this in these embedded intelligent devices, but you are going to see it as a hardware. I'm going to bring it next week. So we talk about this as a microcontrollers or microprocessors, like in the cars. When we talk about the cars, they use what we call the autopilots. These self-driving vehicles, of course, they're embedded with reinforcement learning, where they're able to understand. You're able to trigger those advanced models where you're able to understand, like how does the vehicle be able to understand about the lanes in the major highways, and how is it able to understand what we call the obstructions to avoid what we call the collisions, and many more. Of course, the IoT devices we can use like the drones, and also what we call the robotics. Of course, the robotics, we can use it in terms of sign language interpretation. They are used in the manufacturing to do a lot of processing and many more. And of course, and other appliances use the von Neumann architecture for simple, cost-effective processing of instructions and the data in the memory, in the system memory. For example, here talking about the Arduino Uno ATmega. So I have a powerful tool than Arduino, which is the Raspberry Pi. Yeah. Yeah, it's more powerful than Arduino. So I'm going to bring it next week. You're going to interact with it next week. Yeah, what we call the Raspberry Pi. Let me text you here. Call it the Raspberry Raspberry Pi. Yeah, it's one of the intelligent devices which we use in terms of processing or doing what we call, it's one of the intelligent devices which you use in terms of as an embedded intelligent device, of course, for monitoring. Yeah, the Raspberry Pi. I'm going to bring it next week. Yeah, I'm going to bring that next week, the Raspberry Pi. Yeah, so I think at the end of the session, at least, I want you to get the substance. Yeah, I want you to get the substance. Don't worry about the time aspect and all those stuff. I got you covered. So we are going to understand those things as we proceed. So then we talk about the servers and also the cloud computing. Of course, now for cloud storage, we have the servers which now utilize the shared memory systems to handle large-scale software and also data tasks for services such as the Amazon Web Services and also the Netflix. Of course, this is for video streaming platforms. Yeah. Then, of course, you have the gaming consoles like the PS5, Xbox. Of course, this is more of the virtualizations, and also for gameplay, for gaming, and all those. Yeah. So that's ideally about the aspect about the phone new architecture. Yeah, that's a summary about it. Doesn't have any complexity. That's a summary about it. Yes, Kibet, Brian. Yeah, unmute and.
What is the role of the system clock in that von Neumann architecture?
What is
the role of the system clock?
Or the aspect about the system clock. So yeah. The system clock essentially is able to process what we call when you check in the aspect about the time, the time sets. When we talk about given like the aspect of fetching and decoding your instructions, then the system clock here now we use it in terms of course, processing a sequence of, like in terms of the timestamps. We use it in terms of the timestamps, processing or checking what you call the aspect about the optimal, time processing. When we talk about the time aspect in terms of instruction to be processed in the computer memory, it can be when now you're applying what we call the system or the loop counters. Yeah, what are the aspect about like the aspect about that you're able to hold your data temporarily, and now which means now that's fast in fast out basis, the FIFO principle. Yeah, the FIFO principle which applies when you are processing the series of instructions, which means now that clock is able to send a signal for the first task to be processed. When one instruction is being held temporarily, there's the first come first serve. The first instruction is being processed in that order. Then I think as we proceed, you're going to understand about that clearly, the aspect about the clock aspect. When you are able to hold on that FIFO principle, you're able to hold on the timing, and now we are going to use what we call the cache memory for us to be able to calculate those the timestamps, given a sequence of instructions. Yeah, you get the point.
Yeah,
given a sequence of instructions. Yeah,
for sure.
Yeah, great. So it's more embedded in the cache memory. You're going to see that when you're going to talk about the memory hierarchy. Yeah, you're going to see that. Yeah, or it's not rows. You're going to see that the access time, the time interval. Yeah.
Okay, thank you.
Yeah, great. Thank you for that insight, at least for a great perspective in terms of discussion also. That's fine. Somebody's trying to join in. A few. Then I go to, yeah. Yeah, great. So let's that's now idea about the von Neumann architecture. Now you understand about it. Let me go first about the aspect about the functional components. Of course, it's more information about them in the von Neumann architecture. So let's talk about this aspect. What is this about? The functional components of the CPU memory, input and output devices, and their logical organizations. So here, we talk about these functional components are the CPU, the memory, and also the input and output devices, which are logically organized to execute instructions. So the CPU consists of the control unit, the CU, and the arithmetic logic unit, which is able to manage the operations and also perform calculations. And also we have the memory, which is able to store the data and instructions, where the input and output devices, they're able to handle the data entry and also the outputs, given the input and the outputs. Then we have the system bus, which now provides what we call the communication pathways, which allows the system to be able to transfer the data and also work together in that context. So the functional component of a digital computer system include the input unit, which takes in the data and the instructions, the CPU, which processes the data with this central processing unit, with the control unit, CU, and also the arithmetic logic unit, and also the registers, where you're able to temporarily store your files. So the main memory or the memory unit, it stores the data temporarily, what you call the RAM. So talking about the RAM here now, you're able to store your data temporarily within. Just a second, then we continue. So I'm trying to join in a second. Yeah, somebody trying to join in, Derek. Yeah, others are trying to join in, and the system tries to lock them out. Yeah, so I look for a premium one and subscribe to it. It means now these limitations, I don't want to lock anybody going forward. Yeah, all must be on session. Yeah, all must be on session to be able to really interrogate these technologies and ask questions, and also like get to understand the concept, because now this is the foundation. This is the foundation to the computer systems. So which means I don't want to face anybody out. All must be on board for this session. Yeah, so then here, talking about the RAM, you're able to temporarily store your files. Of course, we have like now, given what we call the HDD, which is the hard drives, and SSD, now you're able to store your data permanently within your device. Then the output, which displays the outputs, which has what you call the display, such as the bus systems, they're able to connect for data transfers within the components, or for them to be able to execute a task and also provide the outputs for all the instructions. So this is ideally the functionality about the functional component of the CPU, the memory, the input and output devices, and also what we call the computer organization architecture. So here now it consists of that, the input, the unit, the memory unit for storing, then for storing information. Then we have the output unit for displaying the results, the outputs, and the pass, which now you're able to connect to all the parts. Yeah, so here now ideally this is the architecture. These are the components here, the input unit. We have the mouse, the keyboard, the microphone. Then we have the control unit. Then where you're able to store or for displaying or the control unit here, the arithmetic logic unit, that part, the output devices. Yeah, so of course, the printers, the speakers, and the internal memory, of course, for the main memory. Yeah, so this is a architectural functional component of the input or the CPU. Then these computer components, we have the input, the input unit, which now you are able to capture the data and instructions from the users and also the external sources. Then you have the function. The function of this input unit, you're able to convert the input or the binary signals, which I said, these binary signals are in form of series of numbers of zeros and ones. Yeah, I know others are trying to join in, but they can't join because the system faces them out. Yeah, I know this. I know this. So going forward, we are going to our physical classes. And I look for a premium one, which now can cut across more than 300 and above. Yeah, it means like 60% of us are not with us for this session, but I got you covered. The content is easy for you to go through it, and I'm going to, you can go through it. And also, I think I have a recording here, which at the end of the session you are going to get. Yeah, that recording, let me check. Yeah, a lot of them trying to join in, they can't join. Yeah. Anyway, so then we have what are the common devices of the input unit? We have the keyboard, the mouse, the touch screens, the scanners, the sensors, the stylus pens. Yeah, that touch pens. Of course, you have the voice assistants, which are embedded with the Siri, Alexa. Of course, these are more of generative AI models, or what we call the strong AIs. Yeah. Later, maybe I'm going to teach you something like machine learning, and you're going to understand those things clearly when we talk about generative AI models. Yeah, supervised learning, unsupervised learning, deep learning models, convolutional neural networks. You're going to understand about that as you proceed with the academic landscape. We have the biometric devices, which now we talk about the face, the fingerprint recognition systems. We have the IoT-based inputs from the smart devices. When you talk about the smart watches, which now you're able to measure like the weight, maybe the distance which you have traveled. Maybe if you're commuting from Graduation Square all the way to Chiromo, what distance have you covered? What kilometers have you covered? Have you reduced what we call your weight? Yeah. Also, like maybe you're checking like maybe am I triggering the sign of obesity and all those stuff. Those smartwatches, they're able to monitor even your eating habits. Yeah. So those are the things which in this domain of AI you should be focusing on. But we'll give you what we call we'll give you the foundation. As we proceed, let's first of all understand these basics. Yeah. Yeah. Then we have the central processing unit, of course, which is the main, the brain of the computer systems. What are the components? Of course, we have talked about these arithmetic logic units, which are able to perform arithmetic operations such as the add, subtraction, multiply, divide, and also the logic operations where you are able to comparison and decision making. Of course, you are able to embed techniques such as the logic gates for digital electronics. And also it's able to support AI and machine learning tasks using built-in the vector and also the matrix operations in the modern CPUs. Yeah, so what we call the modern CPUs now, we orchestrate with microcontrollers, of course, embedded intelligent devices. Yeah, we have the control unit, which now you are able to, it directs the operation of all the computer parts. You are able to decode instructions and also coordinate the data flow. You're able to send the control signals to the memory and also the input and output devices. Then we have the registers, of course, which you are able to, of course, we are talking about this. I think it provides that communication pathways. Yeah, or temporarily storing instructions, addresses, and also intermediate data. Then it consists of the accumulators you have seen from that architectural framework of the CPU, or this. Then, of course, the computers here, we talk about the memory and the storage unit. This unit, memory unit, you are able to hold the data temporarily and instructions before or during and after processing. You have the main memory, which is the primary memory, what we call the random access memory, where you're able to temporarily store the data during execution. Like these are the types of the memories, the matching ones, the matching memory, and also of course, the old one, the traditional one. We have the ROM, which is the read-only memory, which now you're able to store boot up instructions and the firmware set. This is what you call, you're able to store your files, you're able to store instructions and the data. Then an example, we can talk about the cache memory, which is ultra-fast memory. It's an ultra-fast memory. Of course, between the CPU, and the RAM, L1, L2, L3. You're going to talk about this as we proceed with the cache memory, because it's a subtopic of its own. Then you have the secondary memory, which use it for long-term storage, data storage, like the SSD. You have NV, an example of SSD, you have NV, ME drives, HDD drives, flash drives, and the cloud storage. Then you have the modern trends in the secondary storage, where we are able to orchestrate our data, like the hard drives, or Google drives, the cloud integration, and also the hybrid storage models. Of course, you have the output units, which are able to convert the processed data, the binary, into a form users can understand. An example, we can talk about the visual, the monitors, and all those, the printers, the audio speakers, and the headphones. Then, what are these interconnections? How do we interconnect these components? Allow me 10 minutes, allow me 80 minutes. I know, because I know you have another session, I think from 11, right? Just allow me 10 minutes, and like 80 minutes, then of course you can proceed with another session. And what I'm going to do, I'm going to share the slide with you. I'm going to share with you this. What I want you to do, the modern learning system is not about a lot of complexity notes, which are not like you are really struggling to understand the content. I think from these slides, as it goes, it's easy for you to go through them and be able to understand them. There's no complexity there. So let me talk a little bit about this slide, then we finish. I share this slide with you. And next week, when we meet up, we are going to talk about the memory hierarchy organization. We are going to talk about the memory hierarchy organization, where I'm going to mention about what is it about the memory hierarchy, what it is about the cache memory, and the various computer organization architectures, which I'm going to mention later. So here we have, for the computer system, consists of an input that takes input, and also the CPU that is able to process the input, and also the output units that also is able to produce the outputs. So here it consists of this interconnection of the components. The computer system, this interconnection, it cuts across the system bus, where we have the address bus, you have the data bus, and also the control bus. What is it about the address bus? It carries the data, or it carries the address across the data and the location. So this is you're able to carry the data instructions. The data bus, it carries the data from one component to another. And the control bus carries the data, carries the control signals. So we say here, let me put it here for you to be able to avoid a lot of complexity. Bring it here and say the control bus. It carries the control signals. The system bus is a common communication pathway that carries the signal to and from the CPU to the main memory, and also the input and output devices. So the input devices communicate with the system bus through the controller circuit, which helps in managing various input and output devices. That's interconnection. So here now getting to understand about the system buses, which is an example of the control bus, the address bus, and the control bus. So this is the architecture of those functional components, from the CPU to arithmetic logic unit to the registers to the control unit to the memory, then the system bus. Then now here we reach here under the program execution. So let me finish it here. Next week now we focus on what we call the concept about the memory hierarchy. Yeah, we focus on the memory hierarchy. Is that clear? Yeah, I think that's clear. No, so next time now we're gonna focus on the memory hierarchy. Yeah, so don't worry, like, oh, we are lost. Pass out the information for those who are not here. We are going to cover these things, and you're going to get the basics, and you're going to get your coursework assignments and assessments. Yeah. So next week we'll have a physical class session. So I'll be there. I'll ask you the class lab. I'll ask you the class labs for us to look a room prior before. For us to not to be traveling this kind of time kind of inconvenience, also accessing the room on time. So don't worry, you got covered. Yeah, pass how this information. So we are there. You're not going to lose. You're going to get the substance. Thank you for showing up, and for the rest who didn't show up, I'm going to share the slide with you, and I think I have some recordings. Yeah, the slide. The slide, it also covers of what you're going to talk about next week. Yeah, you can read ahead of the curve. Yeah, you can read ahead of the curve. Great. Thank you once again, and wish you the rest of the time well, and for your class session. The rest of the class sessions.